MET 330 Final Exam Study Guide, Fall 2021. Derivations. Even though full derivations will not appear on the exam, small portions of them could. You should be familiar with the equations we worked with and assumptions made in their derivations so you can adapt them to suit your needs. No assumptions and derivations for PGF, thermal wind, hypsometric, and mass continuity equations. Know the basic steps of the vorticity equation derivation. The assumptions for all those equations mentioned are in the Exam 2 Study Guide audiobook, and anything else that's in the Exam 2 Study Guide audiobook will not be mentioned in this aside from in passing. Section 1, Math and Kinematics. Know how to use dot products, cross products, partial derivations, and the del operator. The different coordinate systems and the equations. So for Cartesian coordinate systems, this uses the x, y, and z axes, and it's a fixed system, meaning it doesn't travel with whatever you're measuring. X is the east to west direction, y is the north to south, and z is up and down vertical. Pressure replaces the z-axis with pressure. For example, dv dz becomes dv dp. Remember that pressure becomes lower as you go up in the atmosphere. The natural coordinate system is not fixed. It travels with what you're measuring. T represents the direction in which what you're measuring is pointing, like the wind, while N is the axis 90 degrees to the left of that. Terms and equations. For the equations we saw in Exam 2, you may go back and listen to the Exam 2 study audiobook. Momentum equations. For the zonal west to east wind, you have negative 1 over density times dp dx, which is the pressure gradient force. You have the Coriolis force, which is 2 omega v sine latitude minus 2 omega w cosine latitude. And then you have curvature, which is u times v tangent latitude divided by a minus u times w divided by a. Finally, you have the viscous force, which is k Laplacian of the wind times u. For the meridional wind, it's quite similar. Pressure gradient force is the same, except the x becomes a y. Coriolis force is now negative 2 omega u sine latitude, and curvature is negative u squared over a times the tangent of latitude, and viscous force remains the same except the u becomes a v. For the vertical component of the wind, the pressure gradient force is equal to negative 1 over density times dp dz minus g, which is gravity, plus the Coriolis force, which is 2 omega u cosine latitude, plus curvature, which is u squared plus v squared divided by a, plus the viscous force, which is the same, except the v is replaced with a w. For things concerning the Rossby equation, see Exam 2 study audiobook, and just make sure that you understand and are able to draw vector fields for each of these terms. Section 2, Scale Analysis. Know what scale analysis is and why we perform it. Scale analysis is the process that we use to determine which forces are of relevance when we're calculating something. And we perform this so we know which forces, if any, are negligible. This is to simplify things for us. For the magnitude of different terms of the equations of motion, horizontal wind is 10 meters per second. Vertical wind is 10 to the negative 2 meters per second. Horizontal length is 10 to the 6. Vertical length is 10 to the 4th. Density is 1. Horizontal variations in pressure are 10 millibars. Vertical variations in pressure are 1,000 millibars. And time is 10 to the 5th seconds. latitude doesn't exactly have a scale to it. And the Coriolis parameter is 10 to the negative 4th per second. The radius of the Earth is 10 to the 7th meters. And the kinematic viscosity coefficient is 10 to the negative 5 meters squared per second. Remember that if one term in your equation is at least an order of magnitude smaller than the others, that term is negligible. Section 3, forces in balanced flow. So, for forces in balanced flow, all of the following is contained within the Exam 2 study audiobook. This goes for things like inertial, non-inertial reference frames, recognizing the equations for things like pressure gradients, force, Coriolis force, etc. It also applies to things like the Ekman layer and mass continuity. So, just one note on calculating mean divergence. The mean divergence is equal to, on the top of the fraction, negative dp at the surface divided by negative dt, and all of that is divided by the pressure at the surface minus the pressure at the tropopause. For surface pressure in this equation, take the average of the pressure at the surface at time 1 and time 2. The thermal wind equations are covered heavily in Exam 2 study audiobook, but just a few notes. To calculate delta T given Vt, or the thermal wind vector, you use either the UT equation or the Vt equation, depending on which direction you're dealing with. And in that, delta T is going to be equal to the mean temperature in this equation, either Ty or Tx. So just keep that in mind if you need to calculate one of those. And just keep in mind also that there will not be a problem concerning more than one of these components on a time on the exam. So one of these components, either UT or VT, will equal 0. You should also be able to calculate U and V at a given height, given VT, which is just the standard equations of VG2 minus VG1 or UG2 minus UG1, and those equal VT and UT respectively. Keep in mind that veering is clockwise, and that signifies warm air advection. Backing is counterclockwise, which signifies cold air advection. Vorticity, section 4. The difference between a diagnostic and a prognostic equation is that a diagnostic equation does not factor in time at all. It is for a specific moment. A prognostic equation takes time into account. It can prognosticate what something will be at a given time other than the present, either in the future or the past. So, for the diagnostic vorticity equation, you have vorticity equals V over Rs minus dV dN, where V over Rs is the curvature term and dV over dN is the shear term. So vorticity is the curvature minus the shear in this case. Now, in height coordinates, the vorticity equation is comprised of 4 terms. They will not be read out in this audiobook, but they're available on the study guide, and I will still go over the terms. So, A is the divergence or stretching term. Think of the ice skater analogy here. When the divergence is positive, rotation will slow. And when divergence is negative, rotation will speed up because negative divergence is just convergence. You can't go from positive to negative vorticity purely due to divergence or convergence. You can only get more positive or more negative. B is the tilting term, and C is the solenoidal or baroclinic generation term. D is the friction term. For this, think of how friction is less over a lake than over land. So there will be horizontal wind shear there, which generates vorticity. So, the difference between relative and absolute vorticity. Relative vorticity does not take the vorticity of the Earth into account, and absolute vorticity does. It takes the Coriolis factor into account and is equal to relative vorticity plus the Coriolis factor F. Circulation is vorticity over an area. and is calculated simply by multiplying vorticity and area together.